Quadratic irrationals. Any quadratic irrational can be written as a plus b times root d, or p plus q times root d over r. There's only one way of writing quadratic irrationals in this form, other than trivial variations. Because if we assume a1 plus b1 times root d is equal to a2 plus b2 times root d, where a1 is not equal to a2 and b1 is not equal to b2, then we can rearrange root d into this fraction. And we can see that there's a contradiction, because if they're not equal, root d can be expressed as a fraction of two integers, which is impossible because it's irrational. Therefore, they are identical. Quadratic irrationals will always remain in this form when they're combined using elementary operations of arithmetic, and every quadratic irrational is the root of some quadratic equation of the form ax squared plus bx plus c is equal to 0, where a, b, and c are integers and a has to be positive. Also, its discriminant must be positive as well. Every quadratic irrational also has a conjugate, which is obtained by flipping the sign in front of the square root. The conjugate of the result of any arithmetic operations on two quadratic irrationals is equal to the result involving their conjugates. Reduced quadratic irrationals. A quadratic irrational alpha is reduced if alpha is greater than 1 and its conjugate is between -1 and 0. They are also roots to the quadratic equations in the form of ax squared plus bx plus c is equal to 0, where a is greater than 0. So the conjugate is just the other root to the equation. Alpha must also satisfy the following conditions. P is between 0 and root d, and root d minus p is less than q, which is less than root d, plus p, which is less than 2 root d. Here's the proof. Since alpha is greater than its conjugate, the sum 2p over q must be positive. Now, because q is equal to 2a, q is positive, therefore p must also be positive. Alpha dash is less than 0, therefore p minus root d is also less than 0, and therefore p is less than root d. Alpha dash is greater than -1, therefore p minus root d is greater than minus q. Therefore, root d minus p is less than q. Alpha is greater than 1, therefore p plus root d is greater than q. Therefore, q is less than p plus root d. And by adding up the previous two inequalities, we can see that q is less than 2 root d. An implication of this is that for each value of d, there's a finite number of integer values of for p and q. So there's a finite number of reduced quadratic irrationals for each value of d. This is important later on. Any reduced quadratic irrational can be expressed in the form alpha equals b1 plus 1 over alpha 1, where b1 is the largest integer less than alpha, and alpha is another reduced quadratic irrational with the same value for d. We're going to prove this. So we're going to start from the quadratic equation that alpha satisfies, and we sub in the definition for alpha. Next, we rearrange this equation and get another quadratic equation that alpha 1 satisfies. Next, we solve for the positive root, and after rearranging, we can see that inside the square root, we still have b squared minus 4ac, so d remains the same, but p and q are different. Now we have to show that alpha 1 is reduced. So, since b1 is the greatest integer less than alpha, therefore alpha 1 over alpha 1 is between 0 and 1. So alpha 1 is greater than 1. Next, alpha is equal to b1 plus 1 over alpha 1, and after rearranging, we can see that alpha 1 is equal to 1 over alpha minus b1. And if we take the conjugate of alpha 1, we can see that it is equal to 1 over alpha dash minus b1. And since alpha is reduced, its conjugate is between minus 1 and 0. And since b1 is the largest integer, less than alpha, we can see that alpha 1 dash is between minus 1 and 0. Now we're going to prove that if alpha is a reduced quadratic irrational, it can be expanded into a purely periodic simple continued fraction. Let alpha be b1 plus 1 over alpha 1, and since alpha 1 is also a reduced quadratic irrational, it can be broken down into alpha 1 equals b2 plus 1 over alpha 2 and so on. So eventually we will end up with alpha equals b1, b2, b3, dot dot dot. Since the expansion is infinite and all alpha I have to have the same value for d, there is a finite number of cases for the alphas. Hence, they'll be repetitive. From this, we can say that if ak is equal to al, then ak plus 1 is equal to al plus 1 as well, because we're expanding them in the same way. Next, we need to show that alpha is periodic from the very beginning to show that it's purely periodic. And in order to do this, we're going to prove that if alpha k equals alpha l, alpha k minus 1 is equal to alpha l minus 1. So from what we're already given, we can see that all we need to do is to show that bk is equal to bl. And to do this, we're going to define beta k to be minus 1 over alpha k. Next, we're going to take the conjugate of alpha k minus 1, and we're going to rearrange it to get beta k equals bk plus 1 over beta k minus 1. And we can see that since alpha k plus 1 is reduced, its conjugate is between minus 1 and 0, and therefore 1 over beta k minus 1 is between minus 1 and, 0 and 1. What this means is that bk is the largest integer, less than beta k, and if we repeat this on bl and beta l, we can see that bl is the largest integer less than beta l. And since we already know that beta k equals beta l, we can get that bk is equal to bl. Finally, if alpha k is in the first complete quotient, we can just repeat the following steps. So we go from alpha k all the way to alpha 0, and from L to somewhere, let's define it as alpha s. And this means that once we reach from alpha s from the first partial quotient, the sequence is going to repeat because we're going to expand it in the same way. And therefore, alpha must be a purely periodic continued fraction. If alpha is equal to a purely periodic simple continued fraction, then alpha is the positive root of a quadratic equation with integral coefficients. We're going to prove this, but first let's talk about complete quotients. We can get the kth complete quotient by just ignoring all the partial quotients up to the kth, and the rest would just be the complete quotient. For example, here alpha is equal to a1, a2, a3, dot dot dot, and we are just ignoring terms. Okay, so since alpha is periodic, we can cut off alpha at an by letting alpha to be the rest of the purely periodic continued fraction. So alpha would be the nth complete quotient. And we can now treat it as a finite simple continued fraction. although it is not. But according to the equations, alpha should be equal to alpha n plus 1 p plus p subscript n minus 1 over alpha n plus 1 qn plus q subscript n minus 1. And after simplifying, let's just say it's p subscript n plus 1 over q subscript n plus 1. So after some rearrangements, we get to the quadratic equation below, and we can see that alpha is indeed a root of some quadratic equation. Now, what about quadratic irrationals that are not reduced? According to Lagrange's theorem, any quadratic irrational alpha has a continued fraction expansion which is periodic from some point onwards. Let alpha be b1, b2, b3, ... all the way until up to alpha n plus 1, where alpha n plus 1 is a complete quotient, and we need to prove that it is reduced, because if so, it's going to be purely periodic, which means that the expansion of alpha will be periodic from alpha n plus 1. We're going to say that the final convergent of alpha is going to be equal to alpha itself, and take its conjugate. Next, we rearrange for alpha n plus 1, and we factorize it. We can see that for the second part, as n increases, it's gradually going to tend towards 1. Now, because all partial quotients are positive other than the first, therefore, all the q's are going to be positive other than q1, and the recurrence relation tells us that q increases with n. Therefore, the first part is always going to be less than 1. This tells us that whenever the second part is less or equal to 1, the entirety of alpha n plus 1 dash is going to be between -1 and 0. And since we leave a decimal after each time we take a partial quotient, when representing it as 1 over some denominator, the denominator must be greater than 1 to represent this decimal. Therefore, alpha n plus 1 is going to be greater than 1. We have now shown that the expansion of alpha will eventually end up at a reduced complete quotient, which means it will eventually become periodic.